questions 21 through 25 of the 2002 grade 12 AMC 12A. Consider the sequence of numbers 471, 8976, ... for n greater than 2. The nth term of the sequence is the units digit of the sum of the previous two terms. Let Sn denote the sum of the first n terms of this sequence. The smallest value of n for which Sn is greater than 10,000 is. So we've got part of the sequence that they've already given us, and let's keep going and figure out the rest of it. So what's happening is you've got numbers, and when you add two of them, like 4 plus 7, for example, is 11, the result, you take the units digit, which is the last digit, and that becomes the next number. So if you take 7 and 1, it becomes 8, and 8 is just a single digit, so its units digit is just 8. Same thing, 1 plus 8, it's just 9, so the units digit of 9 is just 9. That's why the next digit is 9. How about 8 plus 9? That's 17. The units digit of 17 is 7, and therefore that becomes 7. Keep going here, 9 plus 7 is 16. The units digit of that is 6, and therefore the next number is 6. So I hope you get the hang of this, but we got to keep going. We got to make the whole list. I don't know how long this is going to go on for, but my hope is that there's going to be a pattern. There's always some pattern in these kinds of questions. So 7 plus 6 is 13. Units digit is 3. So we go 3. Let's see here. 6 plus 3 is 9. The units digit is 9. 3 plus 9 is 12. Units digit there is 2. 9 plus 2 is 11. Units digit is 1. 2 plus 1 is 3. Units digit is 3. 1 plus 3 is 4. Units digit is 4. 3 plus 4 is 7. That gives me a units digit of 7. 4 plus 7 is 11. That gives me a units digit of 1. 7 plus 1 is 8. That gives me a units digit of 8. 1 plus 8 is 9. So that's a 9. 8 plus 9 is 17. So that gives me a 7. 9 plus 7 is 16. So that gives me a 6. I'm just continuing here. I ran out of space. Let's just keep going here. 7 plus 6 is 13. So that gives me a 3. Let's see, what else do we got? 6 plus 3 is 9. So that's a 9. I can do this in my head now. 3 plus 9 is 12. So that means that's a 2. 2 plus 9 is 11. So that becomes a 1. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 4 is 7. 4 plus 7 is 11, so that becomes a 1, and so on. 7 plus 1 is 8, and you get the idea. You can continue to do this. But I did see a pattern here. This repeats itself. It repeats itself right here at this point. Look at these ones. 47189 763 9213. Then 47189 7639213. It repeats itself like that. 4718. So I hope you saw that. This repeats itself. You'll see it again there, right there. Okay, so that's the sequence that I was looking for. So how many terms is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So every 12 terms, it repeats itself. And what is the sum? We have to eventually figure out sums, right? Okay, so what is the sum of those 12 terms, the first 12, S12. If you add all this up, 4 plus 7, 1, 8, 9, 7, 6, 3, 9, 2, 1, 3 is 60. Okay? So that means that if you add the next 12, S24, it'll be 60 plus 60, right? Because every 12 terms is exactly the same. So that's 120. If you go to X36, it'll be 60 plus 60 plus 60, and so on, right? You get the pattern. So that basically means that every S to the 12n is going to be 60 times n, whatever n is. And we have to figure out, according to our question, what is n when the sum is greater than 10,000? Okay. S at n is greater than 10,000. All right. So that means that 60n, because that's basically the sum, 60n is greater than 10,000. So if you take out a calculator, you'll find that n is greater than 166.66. So obviously n is somewhere between 166 and 167. So let's just start with 166 and see what we get. So if n is 166, this becomes S12 166, and this becomes 60 times 166, correct? So S12 times 166 is 1992. And 60 times 166 is 9960. Okay? So when we get to the 1992nd term, our sum is 9,960. But we want to get over 10,000. Okay, no problem. What are we adding? We're adding these terms, right? So let me write that up there. I'm going to write this up there because I would like to see that list. S to the 992 is 9960. So that means right here, S to the 992 is 9960. Correct? So that means when you add the first 1,992 terms, the sum will be 9,960. But I've got to get the sum over 10,000. So how many terms? Well, it's not 1992, so that answer is out because that sum is 9960. So we have to start from here and keep adding. Okay? So this is going to be, that arrow that I drew, is the 199 third term, this 4. Okay? Because I've so far added multiples of 12. That's why I did that. 12 times 166. So get out your calculator and let's keep adding. 9960 plus 4 would be 9964. Correct? You see what I'm saying there? So S to the 993 would be 9960 plus that 4. 9964. Do you see how I did that? So if you continue to add, you'll find that you have to get all the way to here to get a sum greater than 10,000. That sum will be 10,002, and that is 1993, 1994, 1995, 1996, 1997, 1998, 1999. So S to the 1999 is 10,002. All right, so the answer to this question is B. Number 21. Triangle ABC is a right triangle with angle ACB as its right angle. M angle ABC is 60. Measure of angle ABC is 60. And AB is 10. Let P be randomly chosen inside ABC. and extend BP to meet AC at D. What is the probability that BD is greater than 5 over 2? So the good news is they've already labeled a lot of this for us to help us understand it a little bit better. So let's start labeling everything in here that we know. So let's see, this is a right angle, and angle ABC, this guy right here, is 60 degrees, and therefore this has got to be 30 degrees. And we know that the ratio of the angles in a 30, 60, 90 triangle are 2, 1, let's move this over, 1, and root 3. Okay, those ratios are always the same for 30, 60, 90 triangles. And do they give us any other? Yeah, AB is equal to 10. So the actual value is 10. And therefore this has got to be 5, and this has got to be 5 root 3 from those ratios. All right? Very, very common triangle on math contests, and the ratios are obviously very important. And now they're talking about BD. And they want you to figure out, when is BD greater than 5 over root 2? So first and foremost, we'll let BD equal 5 times root 2. 5 root 2 like that. Now, this is BD, correct? That line right there. If you drew BD like this, it obviously would be less than. They want you to make it greater than. So that means BD would be in this part of that triangle. So what we have to do is essentially calculate the area of this region. Once we calculate the area of that region, we divide by the area of the total triangle, ABC, and that will give you the probability. Okay, so that shouldn't be too bad. So first thing I'm going to do is figure out that value right there, x. That's going to be pretty crucial for us. So we can use Pythagoras. 5 squared plus x squared is equal to 5 root 2 squared. Correct? So that's 25 plus x squared is equal to 25 times 2. So this becomes x squared is equal to 50 minus 25. So x squared is equal to 25. So x is equal to 5. All right? So that is 5. And I think that should be enough. So that means this region here is going to be 5 root 3 minus 5. Correct? Because the whole thing, this 5 root 3 represents the whole A to C. All right, I think that's enough. That's all we need actually to figure this out. So the probability, let's recap here, that BD, this line, is greater than 5 root 2, 5 times root 2, is this region right here, divided by the full. So let's do that. So we have that region. It's going to be 1/2 base times height all over the entire one. 1/2, I'll put capital base times capital height. So this region BDA, right here, BDA, that triangle, I can figure out 1/2, the base is right here, which is 5 root 3 minus 5, and the height is from here to here, which is 5. And then the entire triangle, the base is all the way from there to there, which is 5 root 3, and the height is the same, 5. So the halves cancel, the 5s cancel, so all we're left with is 5 root 3 minus 5 over 5 root 3. Yeah. And this looks like the 5s will cancel, so we're left with root 3 minus 1 over root 3. And is that the answer choice? Anything Nope. Most likely they're rationalizing the denominator. They don't like roots in the denominator. So that's fine. Multiply top and bottom by root 3 and we get 3 minus root 3 over 3. 3 minus root 3 over 3. And there you go. 22 is C. Triangle ABC, side AC, and the perpendicular bisector of BC meet in point D, and BD dissects angle ABC. If AD is 9 and DC is 7, what is the area of ABD? We need to illustrate this triangle with the information in the question stem. So this is A, this is B, and this is C. Side AC and the perpendicular bisector of BC meet at point D. So if you're going to cut BC in half, it's going to meet approximately there, like that. So that means this side is the same as that side. And this is perpendicular, so this is a right angle. And so is this one right here. Okay? So that's the first part. BD, so therefore this is D, and therefore BD bisects that angle ABC. So that means if that's X, that's X. Now, from the nature of this, since you have a line that cut BC in half, if you draw lines from B to D and D to C, those will be equal, like that. All right? That's just a fundamental property when you have an angle that is 90 degrees on a perpendicular, it will make those sides the same. So therefore, this is an isosceles triangle, and therefore that is X as well, the angle. And now they tell you that AD is 9, and they tell you that DC is 7. Well, if DC is 7, then BD is 7. Okay? And do we know anything else? I think that's pretty much what we know. Let's continue labeling this. This angle in here will be 90 minus X. And this angle in here will also be 90 minus X, because the sum of the angles in a triangle are 180. And therefore, this in here, since all the angles about a line are equal to 180, this will be 2x. Okay? Because 2x plus 90 minus x plus 90 minus x is equal to 180. And then finally, this angle is going to be 180 minus 3x. All right? So that completes the labeling of this very important diagram. Now I'm going to put two triangles side by side, and I want you to see that they are similar. So these two triangles are A, B, D, and A, B, C. Now watch what happens when I label the angles. This is 180 minus 3x, correct? The angle. This is x right here, and this is 2x. Correct? Just directly from this diagram right here. Nothing new. And then now I'm going to label ABC. This here is 180 minus 3x. Angle B is 2x, and angle C is x. So you see how they have the same angles? And because they have the same angles, they are similar. And therefore the ratio of the sides will be equal. So in this first one, we have AB, which is basically the 180 minus 3x and x side, like that. And if you compare it to the other side, which side is the 180 minus 3x x? It's AC. So those sides have a ratio that will be equal to the ratio of the other sides. So BD in this triangle is the x2x side, and on the other triangle, the x2x side is BC. And similarly, the last side, which is AD, will be equal to AB on this triangle. Okay? So that's the relationship directly from similar triangles. So let's see what we have in terms of values. AB, do we know AB? No, we don't. AC, do we know AC? Yes, 9 plus 7, so 16. And then BD, yeah, we know is 7. And BC we don't know. How about AD? AD is 9, and AB we don't know. Okay, so we can use the fact that this is equal to this to figure out AB. So that means AB over 16 is equal to 9 over AB, like that. So that means AB squared is equal to 9 times 16, like that, which is 144, and therefore AB is equal to 12. All right, so in this diagram, AB is equal to 12. And now we can calculate the area of triangle ABD. ABD, this triangle. How do we figure out the area of the triangle? We don't have a right triangle. We don't have sort of a Pythagorean relationship. We don't really have a height, but we can use Heron's formula. So what is Heron's? It basically says that area is equal to the semi-perimeter times the semi-perimeter minus the first times the semi-perimeter minus the second and the semi-perimeter minus the third. So what do we mean by semi-perimeter? Basically the perimeter divided by 2. So the perimeter in this case is 12 plus 9 plus 7 divided by 2, which is 28 divided by 2, which is 14. So S is equal to 14. So we got 14 times 14 minus 12, which is 2, 14 minus 9, which is 5, and 14 minus 7, which is 7. And this looks like a big number, 980. And 980, let's see, that's 49 times 20. So that looks like 7 root 20. And then root 20 is 4 times 5. So that looks like 7 times 2 root 5. And that becomes 14 root 5. And there you go. We got the angle, the area I should say, 14 root 5. So number 23, the answer is D. Find the number of ordered pairs of real numbers such that A plus BI to the 2002 is equal to A minus BI. All right, so let's make some substitutions. I'll let Z equal A plus BI. And therefore, if you remember, if you take the absolute value of Z, and if it's an imaginary number that it's equal to, it becomes A squared plus B squared, all under the root sign. All right? And then when it's in that form, I'll let that equal S. So root Z, instead of writing A's and B's, I'll just call it S. Okay? So that means the first part there, A plus BI to the 2002, like that, is basically Z to the 2002, like that. And if I'm going to take the absolute value of that, like this, it will basically be S to the 2002. Okay? Those are just some substitutions to make things easier for us. And in a very similar way, we have to look at the second part. I will let Y equal to A minus BI. And therefore the absolute value of Y is A squared plus minus B squared all in the square root sign, which is a squared plus b squared, like that. And a squared plus b squared is basically s. So that means that is equal to s. So the absolute value of y is equal to s. Okay? So now let's deal with this side by side, meaning equal to each other. So we have, we can do it here, a plus bi to the 2002 is equal to a minus bi. Okay? So a plus bi to the 2002 is equal to a minus bi. Let's take the absolute value of both sides. Move this over a little bit. So that means absolute value of a plus bi to the 2002, like that, is equal to the absolute value of a minus bi. So what are we doing here? A plus bi, we called z right here, correct? So that becomes z to the power of 2002, absolute value. And then a minus bi we called y right here. So this becomes y, absolute value. Okay? And then the absolute value of y we called s. And the absolute value of z to the 2002 is basically right here, s to the 2002. So I hope you followed me so far. I wasn't trying to confuse you. I was actually trying to make things easier with these substitutions. So now we are going to work with this. What are the solutions? Well, an immediate solution I see is s equals 0. When s is 0, s to the power of 2002 is 0, and s is 0. So if s is 0, what is a and b? Because they want a and b. Well, s basically, if you notice here, is equal to z, right? Z, the absolute value, which is equal to this guy right there. So I'll write that here. S is equal to the square root of a squared plus b squared. So if s is 0, that means a squared plus b squared is 0. And the only way that's possible if a and b are both 0. That's the only possibility. So we have 1. So the answer choices are not even close to 1. So obviously there's a lot more. The other way this can work is if s is equal to 1. If s is equal to 1, s to the power of 2002 will be 1, and s is 1. So that means that, remember, this is s right here, like that. S is equal to a squared plus b squared under the square root sign. So that means 1 is equal to a squared plus b squared, like that. Okay? We just can square both sides to get that. So now let's bring this over and try to get solutions. We have s to the power of 2002 is equal to s. So if you multiply both sides by s, you'll get s to the power of 2003 is equal to s squared. But s squared is that squared. If s is equal to the square root of a squared plus b squared, s squared is a squared plus b squared is equal to s to the power 2003. And a squared plus b squared is equal to 1. So there you go. Now, what is the solution of this? S to the power of 2003 is equal to 1. It is 2003 complex roots of 1. That is the solution to this. So we had one solution up here, this one, AB is 0, 0, and then we're going to have an additional 2003 solutions, and those are represented as complex roots of 1. 2003 complex roots of 1. So 1 here, 2003 there, so the total is 2004. So number 24, the answer is E. The non-zero coefficients of a polynomial p with real coefficients are all replaced by their mean to form polynomial q. Which of the following could be the graph of y equals px and y equals qx over the interval -4 to 4 for x? So polynomials like p are of the form ax to the n plus b xn minus 1 plus c xn minus 2 plus ... all the way to z. And what they're doing is they're creating a second polynomial where all of these coefficients, a, b, c, all the way to z, are replaced by the mean. So I'll write m for mean. So now you have x to the n plus m x to the n minus 1 plus m x to the n minus 2, like that, all the way ... plus m. Move this over a little bit. All right, so that is what they're doing in the question. Now, what is the mean? The mean of what? The mean of the coefficients of p. So the coefficients of p are a, b, c, all the way till z, right? You have to take those and make a mean. So you have to take the mean of these coefficients. And how do you take the mean or the average? You add them all up and you divide by the number. How many coefficients are there? Well, there's n all the way down to 1, and then there's one final one right here, z, because z doesn't have an x with it. So that means there's n plus 1 coefficients in p. And that is the mean. That is what m is. It's the sum of all the coefficients divided by the number of coefficients, and the number of coefficients is n plus 1. All right? So now we have to somehow figure out the graphs of p and q. How do we do that? Well, there are several ways of going about this question, but I want you to concentrate on something pretty cool, I think, is that what are each of these going to look like when x is equal to 1? So find p at 1 and compare it to q at 1. All right? So if we were to just multiply this, it will be like this. Is equal to a plus b plus c ... plus c. All right? So here we go. Now let's look at p at 1. Why did I choose that? What's special about 1? Because if x is 1, all the x's essentially disappear. They don't disappear in the sense that they make everything disappear. Just the x's would disappear. Watch what happens. P at 1 becomes a 1 to the power of n plus b 1 to the power of n minus 1 plus c 1 to the power of n minus 2 plus ... all the way to z. And this just becomes a plus b plus c. You see what happened there? All the x's go away. So p at 1 is equal to a plus b plus c all the way to z. You see how it made it kind of this essentially the sum of all the coefficients? And the sum of all the coefficients we just did up here. It's m times n plus 1. All right? Now let's do the same thing for q. Let's find q at 1. When x is 1, what is the value of q? Well, it will be m times 1 to the power of n plus m times 1 to the power of n minus 1 plus m times 1 to the power of n minus 2 plus ... plus m at the very end. This just becomes m plus m plus m all the way to m. Well, how many m's are there? There are n plus 1. N plus 1 m's, correct? Because you have n minus 1, n minus 2, all the way down to 1, and then you have one final one. So you have n plus 1 m's. So to get the sum, you would just go m times n plus 1. And do you see something similar? That's the same. So that basically means that p at 1 is the same at q at 1. They're equal. So what does that mean graphically on a graph? It means that when x is equal to 1, the graphs of p at x and q at x intersect, correct? They have the same value. So that is the heart of our question right there. We have to look at those graphs, look at x equals 1, and see which graphs intersect at that point. So let's take a look. A, when x equals 1, this is 1, right? They don't intersect. How about B, when x equals 1? It looks like they do, right there. So let's keep that one. C, when x equals 1, they don't. D, when x equals 1, they don't intersect. And E, when x equals 1, they don't intersect. So by process of elimination, and the only one that matches our findings is B for number 25.